So we're now moving on to the objects of study, to a discussion of that. And we are not really, okay, what we're talking about in math, what we want to study are theoretical abstractions, objects. We tend to talk about stuff, even though what we're doing doesn't reference anything in material reality. But we tend to talk about it as stuff anyway. And we have a particular object of study in mind for these videos, and that is n, the natural numbers. And I want to make it very clear from the get-go that what I mean by this is not just the set 1, 2, 3, ... and maybe 0. Let's include 0. It is that set, but it's also more than that set. When I write down n, I am talking about the set, and I'm going to use the same notation as if I was talking about the set. But I want to make it very clear that I'm talking about the totality of the natural numbers. The natural numbers as a totality in terms of how you use it. What is this thing? It is exactly what you think it is. You know, it's the thing you've been using your whole life. It's what you've been working with. It's what you've been doing on paper. It's essentially what you would have not questioned the existence of probably in grade school or high school. You would have just taken it as a given that there is this thing called the natural numbers that we work with, that we multiply numbers in, that we have an identity, that we add numbers together sometimes, that we exponentiate, right? That's the natural numbers. That we can always add 1 to something, that we can count. It's the thing we've been using our whole lives, but the totality of it, not just the set, but the structures on it. And the structures within it, right? Primes, divisibility, things like that. And as an object of study, not just as a set, but as something that we're aware of the existence of prior to studying it, and are interested in discovering truth about. Now, so the answer is, what is the object of study? For us, it's n. And what is n? Again, just to reiterate, n is, for our purposes, for the next few videos, exactly what you think it is. So let me write that down. What is n? It's what you think it is. Don't overcomplicate it. That's the whole point, to not overcomplicate it. That's what's going to keep things simple for us, at least for now. This is the Platonic bargain. We are going to be Greeks, and we are going to just assume that this thing exists to study. We will not always be Greeks. Once we've gotten to the first incompleteness theorem, we will back up and try to get ourselves out of this. But I think to begin, it's a lot simpler to just be Greeks, just to like, and I'll talk about why that's more natural once we're done with it too. But for now, the natural numbers are a thing we want to study, and when I say the natural numbers, I mean all of it. Don't overcomplicate it. It's what you think it is. We don't know about it. We know it exists. We've worked with it our whole lives, but we wanted to learn more about it. We want to study it rigorously. That's the goal. And so what we're going to do in this video is define a few things that are important, do a little bit of housekeeping, and we're going to do a bit of housekeeping under a new kind of understanding that we've been working with this thing the whole time. So everything I've done with numbers, which admittedly isn't a whole lot, up to now, has been working within this thing, has been working within this model of the natural numbers, this object. So what's the consequence of this? The consequence of this is that if the natural numbers exist as like a Platonic entity, then so do truths about it. So do truths about it. I made a big deal in the last video about how the strings I was writing down were just strings. They had no semantic meaning. Despite, I wanted to make it a big deal that, like, this plus sign was just a piece of text, right? It was this plus sign here, despite you being inclined to think things about it, is just text on a page. And I think that was valuable to do. But the Platonic bargain, the main giveaway that we get from it is that we can simply interpret this plus in the usual way. So I just wanted to be very clear that when we write down like 3 plus 5 equals 8, oops, we are assuming about this plus something. We're assuming things of this plus. This piece of text plus is a signifier for an actual existing, like, Platonic notion of addition, which I am assuming exists, and that comes along with assuming that this thing, this totality, exists. In other words, any well-formed formula that I can write down, has you're tempted to interpret it in a certain way, and so I'm giving you the pass to do that. You're allowed now to do that. So I just wanted to be clear that what the text we're writing down under this, like, kind of Platonic paradigm is only signifying things about a theoretical thing which sort of exists in its own realm. So there is a plus, there's a symbol plus, and then there's the notion of addition. And this plus merely references that notion, and we're trying to discover truth about that notion. But what we can say now is, and what we can assume only for now, we will, again, like, the Platonic bargain will be broken. We will kill Plato later, or we'll try to. But we will assume for now the usual interpretation of all the well-formed formulas in the language of number theory. In other words, all of any formula that I write down that is a well-formed formula, you are allowed to interpret it in the usual way. Anyway, so let's look at a few of them. So, for example, we've got y equals x plus z plus 8. So you might be tempted to, plug some things in and try to solve this for x, and, find an x, y, z that makes this true. And you can think about plus exactly how you're used to it. Same thing with less than, and so forth. But I want to ask a particular question about these examples I wrote down. So, if the well-formed formulas, the syntactical kind of strings from the last video, are supposed to kind of have meaning with respect to the natural numbers, the Platonic entity, then we're going to have to figure out which ones of these well-formed formulas should correspond to claims that are either true or false. Is it all of them, or is it some of them? We haven't thought about that yet, and we need to. So the answer is no, as far as it's not all of them. Not all of well-formed formulas amount to claims. For example, well, I mean, this is a claim here. This is true or false. But let's look at ones with variables, right? Stuff like this is easy to think about. I could write 3 plus 5 equals 9, and I would have a whiff that also works. I don't know why I wrote that down, but I mean, this is another thing that is a statement, right? This is a claim that's true or false regarding n. It's false here, it's true here. But let's throw in some variables and see kind of what we can talk about there. So phi. Is phi phi is a well-formed formula. Is it a claim that's true or false? The answer is no. Why is the answer no? And the answer is it's very simple. It depends on what the variables are, right? I can plug in things for x, y, and z, and they might make this true or they might make this false. Same thing for alpha here, right? I'm throwing around variables. If there's variables, why would it be a statement that's true or false? And the answer comes with this psi right here. Is this a statement that is true or false? By the way, this means or. So what I'm really saying here is x less than y or y is equal to z. But anyway, moving over here. This psi is interesting because it is a statement that's true or false despite having variables. What's it saying? It says there exists an x such that for all y, y is less than x. In other words, what this amounts to is the claim that there exists a biggest number. Right? There is an x such that all other numbers y are less than it. So obviously it's false, but it is a claim that is true or false. And so we're going to have to identify the difference between this kind of usage of a variable and this kind of usage of a variable. Eta is a mixture of the two. By the way, this is my favorite Greek letter. It's so pretty. I love etas. Eta is the statement there exists an x such that x squared plus y squared plus z squared equals 1. And I know I didn't kind of come up with notation for the squared here, but you could just as easily write like y times y instead of y squared. So that's just shorthand. So here, this is a statement, and its truth varies with variables, but it doesn't vary with all of the variables, right? It only varies, the truth of eta only varies with y and z. It doesn't vary with x. And why is that? The reason why that is it's because of this there exists quantifier here. In other words, x here, unlike y and z, are bound by the scope of this quantifier. They are bound inside of this quantifier. X is sort of like a dummy variable. It's used as a variable, but it's only used for the purpose of making a statement in general about the natural numbers. Y and Z are different. Y and Z supposedly reference something, who knows what. So it's a completely different use of these variables. The usage of x and eta here, and the usage of x and y in psi. If you've ever taken like calculus, you've seen integrals that use this, right? Integral from 5 to 6 of like x squared dx. If you don't know what this is, don't worry about it. But if you've seen something like this, then you know that this is a number. This is a single number. And so this x, even though it's a variable, is only being used for the purpose of processing a number into an integral. So it's a dummy variable here too. And this is a dummy variable in the same way. Over here, the usage of this variable is bound inside the scope of the integral, whereas the x over here is bound inside the scope of this quantifier. It's kind of the same thing going on. It's a free variable, or it's a dummy variable, not a free variable. It's the opposite. So it comes down to the variables. So psi is a true or false claim because it has variables which are psi is a true or false claim because it only has variables which are accounted for by quantifiers. Right? All of the variables in this expression, y and x, both have a quantifier, sort of, a guardian, just hanging out, just making sure it's okay, taking care of it. It has an adult with it, is kind of how to think about it. So these are bounded. We say that x and y are bound by their quantifiers. They are bound by the scope of the quantifiers. Likewise, in eta, x is bound, but y and z are not, and we call those free variables. So we have bound variables, which are within quantifiers, and free variables. And so we have our answer. In terms of what well-formed formulas involving variables correspond to claims that I should interpret as like statements that might be true and might be false, the answer is the statements, or the well-formed formulas which only have bound variables. In other words, don't have free variables, or don't have variables which are not within quantifiers. So here's my definition. A well-formed formula with no free variables, i.e. no variables which aren't accounted for by quantifiers, is called a sentence. So if all the variables have parents in terms of their guardians, in terms of quantifiers, then we call it a sentence, and we can interpret it as a statement that's true or false. And so now that we have this, we've identified the whiffs that kind of matter in terms of true or false. That's not to say that the other ones don't matter. These will matter. We're going to talk about them very shortly. But they just serve a different purpose. But the sentences are the statements that are true or false. And so we have this Platonic object. I'm avoiding going on to this red zone here. We have this kind of Platonic totality of the natural numbers. We have statements that we are interpreting as true or false. And so we're going to state something incredibly important for the record that's, at this point, will seem kind of silly to say out loud. It's like, did you really need to say that? And the answer is yes, I did need to say that, because it's incredibly crucial to note this, because it will get confusing later, and it also is a crucial fact, which will kind of, you'll see how it's crucial. Here's the assumption. It's simple. Every sentence is either true or false for the natural numbers. If I have a sentence, this thing that I can interpret as a claim that's true or false, then it is true or false for this thing, this Platonic ideal of the natural numbers. So if phi is true, then we have some notation for it. We'll write that n, and then this line with 2 bars here, phi, with a phi. And I know this kind of looks awkward because the interpretation of it for us, how we're going to read this out loud, is phi is true for n. So it's like we're reading right to left, which is kind of odd. The reason that it's like that is because later on we're going to talk about these things called models in an attempt to kill the Plato inside of all of us. And the extent to which we will succeed at that is up for discussion. But anyway, in any case, once we get there, the way that this will read will be n models phi. N is a model, and phi is true within it, so n models the statement phi. So I wrote it and crossed it out here, but the way I want us to read it is phi is true for n. The whole point of this Platonic bargain is to avoid talking about models, at least until we start to get into the second incompleteness theorem. You can get all the way to the first incompleteness theorem without any reference to models by being a Greek, by doing this Platonic bargain that I'm talking about. And that, I think, makes things a lot less confusing, because models are pretty confusing when you first see them. If you don't arrive at them kind of naturally in the way we're going to. I think I'll make models a lot more clear by kind of getting to them in the way that we're going to get to them. Anyway, so this statement is obviously false, that there exists a biggest natural number. But note, phi is either true or false. Another way to say that is that either phi is true or not phi is true. And so n still not psi is true for n, right? It is not the case that there exists a biggest natural number. In other words, for all natural numbers, there is a natural number that is bigger than it, right? Flip this, and then flip this around, right? That's how you negate a quantified expression like this. Let's consider eta, though, right? Eta has one bound variable and two free variables. It becomes, I want us to know, we're going to talk more about, I think we're going to talk about these kinds of formulas, the ones that have free variables, in the next video. But one thing I want to mention about them right away is that they do become sentences if we plug in constants for the y and the z. I can kind of, these are variables, right? The whole point is I can plug things in for them. So if I plug in y equals z equals 0, then eta becomes a sentence. Everything is suddenly bounded now that's left. I just get there exists an x such that x squared is 1, and that's true, right? Pick x equals to 1, and you're done. So this is a true statement. This is a sentence, and it's true if I just plug in numbers for the free variables. And so we can sort of think about statements like eta, or phi, or alpha, above here. We can think of these as functions that we can plug numbers into and get a truth value out. I can plug in an x and a y and a z, and alpha will end up being a sentence that is true or false, depending on what I plug in. And so any well-formed formula can become a sentence if I plug things in for its free variables. And I'm going to kind of think of them that way. This notation exists in the metamath. This is not a thing that I'm going to discuss as an object. This is a notation for me to communicate with you. And essentially what it means is that it's eta interpreted as a function of y and z. I can plug things in for y and z. So I can plug in 0, 0 for it, and that gives me this expression here. And this becomes a sentence. And so I can kind of think of any well-formed formula which has free variables as a function of those random variables, or maybe more precisely, a relation of those free variables. And that is kind of what we're going to talk about in the next video, is the other purpose served by the non-sentences. So we have sentences which we interpret as claims that are true or false, and then we have the other ones, and those serve their own purpose. Those define what we call relations or sets. And so we'll talk about that in the next video. But before I get to that, I want to mention one more extremely important thing. I want to define, we are now in a position to define the most important decision problem of this entire series. So we can now define the crucial decision problem. Remember those? We're going to define a decision problem out of what we said. The decision problem I'm going to denote like truth. Truth with like the subscript n. It's the problem given a sentence, phi, is it true for n? And so that is the decision problem. Is it the case that n that phi is true for n? Right? It's this question right here. And as a set, it's kind of clean. I can write out, as a set, it's simply truth of n is equal to the set of all sentences phi such that phi is true for n. And so this is our decision problem. These are sentences, not just whiffs, but I'm not going to say that. Oops. So this is the subject. This is the object. I don't know what subject or object. This is the most important thing. This is the thing that we are going to be focused on for the rest of these videos. What is the computability of this, if any? That's what we want to answer. So The rest of these videos will be an investigation of that.